this. There we go. So now we're recording. So if you guys remember, I pointed you to 4 problems that were what I felt were representative of things that we had gone through since we started this portion of the class. So if you remember, we ended up at stoichiometry with the last portion of the class, and now we've moved on into solutions, solution stoichiometry, gases, gas stoichiometry, thermochem, thermochem stoichiometry. So sadly, stoichiometry will mostly be ending for us at the end of this test. I know you're heartbroken, but life will go on. But at any rate, we're going to have, so we're going to go through these 4 problems. I have them worked out here, and you guys will get access to these PowerPoints after class today. Hopefully, and the best thing you can do for yourselves, especially in this modality, is try classes before going through any kind of class like the one we're going through now. It's much better if you come to class prepared. I was saying that when we're face-to-face, and it's no less true when we're online. Try things before you hear about them. It means that you're prepared to learn as opposed to just sort of putting yourself in front of a fire hose of knowledge. It's a much better way to drink. Okay, so what I'm going to do here is share my screen, and I'm going to go through, there are 4 problems here. I'm going to start at the the solution stoichiometry one. So I'm currently sharing my screen. And what you guys should see is the problem that I wrote. So there are 25 mils of strontium nitrate, and it's got a concentration of 3.25 molar times 3.25 times 10 to the minus 3rd molar, and it gets added to 55 mils of a 4.5 molar solution of potassium sulfate, and you're going to form a solid, and what mass of that solid is for. So one of the things you should realize about a problem like this is that it's limiting reagent. You have enough information to get moles on more than one thing. So you can find moles on, and let me annotate, use the spotlighter and hide this thing. Okay, so, so we have volume and concentration of one substance and volume and concentration of a second substance. That means we can get moles on more than one thing. And our first job, if we're never given one, is to write a chemical equation. So hopefully it's been described, and it has. We have strontium nitrate, so strontium a +2 cation, nitrate a -1 anion. And we have potassium a +1 cation and sulfate a -2 anion. Check out the chat. Carlos, I'll come back to your question about that in a second, okay? All right, so what mass of solid product forms? So, so here's our potassium sulfate, and then these things switch. So potassium will go with nitrate, and then strontium will go with sulfate. So we have a +2 and a -2, so we only need one of each, strontium sulfate, and a +1 and a -1, so we only need one of each of potassium nitrate. However, we have 2 nitrates and 2 potassiums on this side, so we need 2 potassium nitrates on this side. So that's our equation, then identifying the solid between those two. All sulfates are soluble except for those of strontium and some others. So this would be solid here. As I mentioned before, I do not expect you to memorize the solubility rules, but I do expect you to be able to work with them, especially if they're given. And they kind of are in the open book way that this test is being going on Monday. So you are being asked to determine the limiting reagent and to calculate the mass. So the first thing we really should be able to realize here is that we have the ability to get moles. So molarity times volume is going to give us moles. So what I do is I take my molarity for my strontium nitrate, because that was written first, and the volume of my strontium nitrate, because that was written first. And for every 1 mole of strontium nitrate sulfate that gets formed, I use 1 mole of strontium nitrate. So it's a 1-to-1 mole ratio between those two. And every mole of strontium sulfate goes to give, weighs 183.672 grams. I go through and do the math on that, and I come out to 0.0149. So if all of my strontium nitrate reacts, that is the most strontium sulfate I can make. What I don't know is how much I can make if all of my potassium sulfate reacts. And I need to figure that out because I have enough information to do so. So I don't know that this is the limiting reagent just yet. So when I go through and I do this with the other stuff, potassium sulfate's concentration here, multiplied by its volume, I have 1 mole of potassium sulfate for every 1 mole of strontium sulfate, and every mole of strontium sulfate still weighs 183.672 grams. And what we end up getting here is 0.045 grams coming out. Now this number is large, so if I was to make this much strontium sulfate, I would actually need more strontium nitrate than what I was given. So this, because the smaller of the two numbers, is my limiting reagent. And that's the answer for this problem. There are 3 significant figures given here, and there are 3 significant figures that are given here. So that's what we would come to with respect to an answer. Now, it's been a while since we've done a problem like this, but I hope that most of the things that are in this problem feel familiar. So I can escape out of that. I'll stop sharing my desktop, come back here, give you guys a chance. If you want to unmute yourselves and have a question and ask a question, this would be the appropriate time. Who has a question over the problem that we just did? If anyone. Okay, so there's one question here in the chat. When using conversion between torr and atmosphere, the 760 conversion is 2 significant figures. When using the gas equation, should the final answer be in 2 significant figures? Curlis, the answer to that is no. It's more exact than that, so you can go beyond 2 significant figures. Generally speaking, you can use the significant figures of what you're given. Okay, so I hope that answers your question. Chat's another good place to go through and ask some of those questions as well. Any questions on the problem that we just did? Because you got the gas law one, I believe, would be next. Pausing for questions. Pausing for therapeutic sip of coffee. Okay, let's move on to the second problem then. Oh, good, glad that answered everything. Okay, so moving on to the second problem here. I'm going to share my desktop again, and we are doing gas law. Okay, I'll click on here. Sorry for the graininess of this. I thought I was going to be able to rig up a document camera, and when that did not look like it was going to work, I cleaned up with this relatively quickly. So let me get the annotate tool back here. Spotlight. Good. All right, so you're given a reaction here. Iron plus sulfuric acid goes to make iron 2 sulfate and hydrogen gas. So what volume of hydrogen gas can be made at 25 degrees Celsius and 0.98 atmospheres when 1 kilogram of iron reacts with excess sulfuric acid? And the thing we need to realize for this is that we have enough information to get moles of iron. We were given a mass, 1 kilogram of iron, and we can use that to determine moles of H2. So this is what our stoichiometry does for us. If I know moles of one thing in a chemical reaction, I can get moles of anything else. So that's exactly what I want to do here. Starting with 1 kilogram, I sort of laid out what my units are going to be. So kilograms will be converted to grams, grams will be converted to moles, and my moles of iron will be converted to moles of hydrogen. Now, luckily, everything here is 1-to-1. This is balanced as written. So when I plug in my numbers here, 1 kilogram is going to be converted to grams pretty easily, 10 to the 3rd. And then 5.85 grams of iron is the equivalent of 1 mole of iron. So that's our gram to mole conversion. And then 1 mole of iron is equivalent to 1 mole of hydrogen. So when I go through and do that, I get 17.905 moles of hydrogen. That seems like a large number of moles, and I suppose it is, but we're starting with a large amount of iron, 1 kilogram. So it shouldn't be a big surprise. So that's how many moles of hydrogen I make here. Now, you want to resist the urge to turn this directly into grams, because that's what we spent the first several weeks of the semester doing. What we're going to do is we're actually going to take the moles of hydrogen and turn that into a volume of hydrogen using the ideal gas law, PV equals nRT. So if I know my moles of this, and I do, R is always given. If I know a temperature, and I do, 25 degrees, and a pressure, which I do, 0.98 atmospheres, the only thing I don't know is volume. So it's a simple matter of plugging things in and finding out what it gives me. So when I do that, the volume is nRT over P, just solving this for that. So my number of moles times R times T divided by P will give me a volume. When I do that, I come out to 447 liters of H2. So given this information, we can figure out how much gas of something we should be end up making. I'm going to pause there for a second. I'll stop sharing the screen. And hey, there's Nai. Hello. So I'll pause that and ask if you guys have any questions over anything that you saw worked out in that problem there. And this would be a good time. You guys can unmute yourself and let me know if you have any questions. Okay, we're up to 16 or so participants. Not bad. How are you guys doing in general? You're all okay? Are your other classes going okay? I can't hear anything. I'm assuming that all of your answers are like, yeah, aces. Everyone's doing great. Got some chat. What's that? Oh, more chat. Yes, thank you. Yes, that's okay. Good. I'm glad to hear that. I really am. This is a weird time for everybody. Going online is probably not what everybody wanted to do, though it is safe. But it's not normal, that's for sure. Okay, I am going to go on into the next problem. Now, the next problem we're going to go into, I did a video on this one. It's with the class. You hopefully have watched it and worked a problem or two based on it. But I'm going to sort of show this now. So this will be the problem where we work with specific heat. So I'm going to share this portion of my desktop. Oops. Click here, F5, annotate. Did I do that right? Okay. Slide this up here to the top. So if I have a 5-gram sample of aluminum pellets, C is 0.89 joules per gram degree Celsius, and they're heated to 100. Actually, let me do the drawing one, because there should be a dot here. It just didn't come through. It's a line. Anyway, there should be a dot right there, 100.0 degrees Celsius, not 1000 degrees Celsius. Okay, so there's that. And it was dropped into water, 97.3 grams of it to be specific, and its specific heat is 4.184 joules per gram degree Celsius, and its initial temperature is 22 degrees Celsius. So what's the final temperature of the water in the metal? A couple things just about the problem. This is a heat transfer problem. A hot thing is dropped into a cold thing. The hot thing here is aluminum pellets, and the problem very graciously gives you the specific heat of it. Now, if you're not given the specific heat, but you're told what the material is, that means you can look it up. And so there's a table in your book, Intro, that has a lot of these listed. In some problems, you'll actually be asked, what is the specific heat of this substance? And then you can, you're actually given the information to calculate it. But in this problem, you're given it. And then for water, we use this one so much, people end up committing this to memory, 4.184 joules per gram degree Celsius. So at any rate, we set this up. The heat that is gained by the water is equal to the heat that is lost by the aluminum. So we have these two Q's. And a negative sign is right here. So the way you actually write this is Q of water plus Q of aluminum is equal to 0. And then we subtract 1 from either side, and a negative sign follows whatever we subtracted. So in this case, we subtracted the aluminum. So there's that negative sign there. So what happens is when we plug in all the variables that make up this Q, mass times specific heat times final minus initial temperature, when we do the same thing here, mass times specific heat times final minus initial temperature, and we take that negative sign and add it in, these two guys end up coming out the same, and then these two guys end up getting flipped. So for whatever's getting colder, and that's what the case is here, it's initial minus final, not final minus initial. Okay, so plugging in the things that we know, I know the mass of water, 97.3. I know the specific heat of water, 4.184. I don't know the final temperature of water. I want to, so I put in a variable for that. I know the initial temperature of water, 22 degrees. On the aluminum side, I know the temperature of aluminum. Sorry, I know the mass of aluminum. I know its specific heat. I know its initial temperature, 100, but I don't know its final temperature. And you can see here, I crossed something out. Here, I almost wrote final minus initial, which would have created problems for me. I'd get a nonsense answer. So what I've got now here is what happens when I start doing the math. So these two numbers here, they're just numbers. I can multiply them. And when I do 97.3 times 4.184, I get 407.1. And then I can distribute that with the two things that are in these parentheses. Excuse me, it's very exciting. So 407.1 final temperature minus 407.1 times 22. So that's where this number comes from. So just distributing this product. That's equal to the product of 5 and 0.895. So, and then multiplying it by 100 is 445. And by itself is 4.45 times TF. So now I've got this expression, and all it is just trying to get the TFs on one side and the numbers on the other side. When I do that, if I get both TFs on this left side here, I get 411.55 TF. And if I get both numbers on the other side, 9401.3 is what I get. I just divide both sides by this 411.55. When I do, I get 22.8. And that number makes sense because it is between the two numbers I started with. It is warmer than the cold water that this hot aluminum was put in. And it is colder than the temperature of the hot aluminum. So that makes sense. It should be between these two. How between is really a ratio of their specific heats. This has a very high specific heat, water does. So it takes a lot of energy for it to heat up and change its own temperature. This has a very low specific heat. It gives off its temperature, or it gives off heat. Excuse me, very, very readily. So that's why this goes down in temperature a lot and this goes up in temperature only slightly. So water is a pretty good absorber of heat. Okay, so I can escape out of that. I can stop sharing my desktop, come back here and see how you're all doing. Sarah asked me how I've been. I've been okay. Been busy. I've been okay. Thank you for asking. Are there any questions on that one? Now, that is one we have not done as a class, and hopefully you've attempted something like that. Watching me do it is not the same as you guys trying it yourselves. Do make sure that you are doing these problems. You're getting them right, or even better, you're getting them wrong and trying to figure out why and how. That is where real learning happens. But watching me do them does not mean that you know how to do them then. You do need to absolutely try this on pencil and paper. Does it matter which side is flipped as far as the change in temperature, or is it always final minus initial on the left and initial minus final on the right? Question from Kim. Excellent question. Let me go back to sharing my desktop. Let's see, I'm gonna go back to specific heat. Share this. Great question, Kim. And so long as you are consistent, it does not matter. So I put a negative sign in front of whatever's cooling down. And for that one, it's initial minus final. This being on the right-hand side has nothing to do with it, okay? I could have put the negative on the left-hand side here with the water, and then that would flip this initial and final temperature. So long as I am consistent. So wherever the negative sign goes, that is where the initial and final gets switched. Left or right side of the equal sign does not matter. It just matters that you're consistent. Excellent question. Thank you for asking. All right. We've got one more question to work through. Any others for you guys? Pausing again for a sip of coffee. Okay, well, let's go to it. This is a Hess's Law problem. It'll take a few minutes for us to work through. And again, this is another one that we have not done together as a class. So I worked one out on the video. So this one's got 9 slides because I tried to really be explicit about how it gets done. Let's click here, F5, annotate. Okay, so given these equations here, 2CLF, I'm not gonna read them all out, but this equation here that has this heat, this equation here starting with CLF3 that has this amount of heat associated with it, and this equation here that has this amount of heat with it. Just looking at these here, 2 of them, these 2, are what? Endothermic or exothermic? Give you a second to think about it. If the number is positive, these are endothermic. If the number is negative, is exothermic. That means energy is a product in this one and energy is a reactant in these 2. So that's what that means. So given all of this information, what I need to do is I need to find out the energy that's associated with this reaction. CLF plus F2 goes to CLF3. There's enough information in all of this for me to do that, but what I'm going to need to do is make a few changes here. So the first change is what my goal is to arrange these three equations in such a way that everything is in the place where I expect it to be. So this ClF3, I need to find that here as a product. And the unfortunate thing is here, it's not a product of any of these reactions. It's a reactant here in the second one, but I need it to be a product. So to do that, what I'm going to have to do here is flip this reaction around. And when I do that, these two products will become reactants, and these two reactants here will become products. And come on now, go away. And this, no, I said go away, not my email. And then this right here will become negative when I do that. So if I run this reaction in reverse, what's going to end up happening is the energy that would have been on this side is now going to end up being on this other side. So it ends up being reversed. So that's the first thing I do. I reverse that first reaction. Okay, and that 341 becomes negative 341. Now I'm going to look for this F2, and I need it to be a reactant. And here it is as a reactant. I've got two of them. I only need one here, but at least it's on the right side, so I don't have to flip this around. So that's good. So now I've got to look for the ClF, and I find it right here as a reactant. And that's good because I need it to be a reactant. That's what it looks like right there. So I've got this ClF and O2, and it's going to Cl2O and F2O, and it's got this energy associated with it. So it's on the correct side. I've got too many of them. I've got two, I only need one. But again, it's on the right side, so I don't need to do anything with it. So I've got all three of these things here, and they're in the right spot. That's good. So now what I can do is I can add these reactions together and see what the energy comes out to. And when I do, hopefully things that are on both sides of this will start to cancel out, because you see a lot of oxygen in these reactions. Well, there's no oxygen in this reaction up here, which means that everything that contains oxygen will hopefully cancel out. So first I'm going to pay attention to just actual O2. I've got two of them here on my reactant side, and I happen to have two of them there on my product side. So they cancel out. They're on both sides, so they effectively are not part of the reaction. Next is F2O. I've got one right here and two right here for a total of three, and I've got three over here. So again, they cancel out. Now hopefully, because I need F2 and I need ClF, I just don't need this Cl2O. And I've got one over here and one over here, and lo and behold, they'll cancel too. So both of those are gone. And when all those are gone, all that I have left are F2 and ClF on my reactant side and ClF3 on my product side. And that's all I want. So when I add those together, I can add these energies together. And I get negative 217.4. Good. That's what I'm looking for. But instead of 2F2, 2ClF making 2ClF3, I just need one of each. So I can divide all this by a common multiplier, which is 2, a common factor, which is 2. So 1/2 of this, 1/2 of that, 1/2 of that, and 1/2 of this. And when I do that, great. Oh, that's just nice. On the last part of that slide too. At least I got to the answer. Let me see if I can open that up there. But as I do you guys have any quick questions over what you just saw most of? I don't know why that happened. Okay, so I recovered all my documents here. So let me just go back and share here one last little bit. I apologize for that. I don't know what happened. That was not my error. So I share my screen. Hess's law. So when I take this reaction, I multiply it by 1/2. I use half the energy, which means 108.7 is what this comes out to be. So that's how I get from these three expressions to this expression and the energy value associated with this expression. The cool thing about this is if you're into modeling, this is how you might actually model the thermodynamics of reactions that you don't have the capacity to do. If you have the capacity to do these reactions, and you can figure these things out. Then you can use these reactions to determine what this one should be. And then maybe someone else with the capacity to do this would confirm your answer. So theory, modeling, experiment has always been like a really good thing in the sciences. Okay, so I've got a little more than 5 minutes remaining of the pre-licensed lecture time. Let me pause here for a quick second. I think I'm not sharing my screen right now. Do any of you have any questions on anything you saw in these 4 questions? They're representative of the things that we've gone through in sort of like big topic areas. So any questions on any of those there? If you have one, just unmute yourself and ask. Okay, no questions. That's fine. What bring the equation down? Does the coefficient and subscript not, when you bring the equation down, does the coefficient and subscript not matter? So let me share my screen a second and showcase that. And I'll use my last slide to show it. I hope that works. Okay, so when I bring them down from here, the subscripts don't change. So if you notice, like this one that I actually did swap around, so CLF3, CLF3 is still there. So all the subscripts are there. I don't get to change those, otherwise I change what the molecules are. Also, the coefficients, I don't get to change those from here to here. So all I'm doing here is either turning them around or using them as is. I do change these coefficients when I multiply it by 1/2, and when I do, their energy drops by 1/2. So the coefficients matter, because if I'm changing the coefficients, that means I'm changing this value. I don't get to change the subscripts. Those are locked in place. Okay, so I hope that helps Kim a little bit. Will I send this copy to, yes, I will. So the question is, will I send a copy of this session for anyone who came late? Yes, I will. All of these, I turn them into a file, and it gets either both the audio or audio and video, and then both of those are uploaded to my courses. So hopefully you guys are checking in with my courses a lot more regularly now than you may have in the past. That's one thing. We had a question about quiz 6, number 7. I can answer that in a little bit. Let me finish through this here. Okay, the other thing I want to talk about really quickly is the test. And the test that I have to go through is, so it's going to be on Monday, becomes available at 12:01 a.m., ends by 11:59 p.m. You should expect about 15 questions on there. And one of the things that I did today is I posted up an exam prep sheet. And the exam prep sheet is fairly representative of what a test can look like. There's 20 some odd questions on there. They're all numerical. Some of the questions you'll see on your tests are going to be multiple choice. But these are questions that you should work through. So that prep is available to you from now. It's been available for the past few hours. And it will go until Monday at 12:01 a.m., the same time your test goes up, and then it becomes unavailable, and then your test begins. So you can take your tests there. This question isn't related to the questions, but I saw a new tab in my course. It's called Honor Lock. What is that? Good question, Wesley. I've not explored that. I'm not using it in this class, but it's basically an artificial intelligence program that is supposed to cut down on cheating. So that is something that I do not have the bandwidth to try and work into my class right now. So it's nothing that I'm using. Another question, to get the enthalpy, why is it internal energy plus pressure volume? Curlis, that's a question we're not really going to get into for any sort of test, but in short, that's the definition of enthalpy. It's and it's simplified when it's constant pressure. So it's effectively heat energy, and that's all that we really go into it on that. So I hope that hand waving kind of answers your question. Mina, I'll have to look up. It's going to take me just a minute to find the question that you're asking about. Oh, but luckily I'm in there, so I can go to these questions. But for everybody else, where class is more or less done, and my session is, of course, expired. So, so Mina, what is your question on the last question on the quiz? And if you want to unmute yourself, that would actually be very helpful to me. Because I have to look at this question as well.
So on the test when I submitted it, it said I got 100%, but then when I checked,
okay. So that's a great question. Is that a question about a question?
Well, on Pearson it said it was right, but then it said it was wrong. So I was confused what that meant.
So it's wrong. Okay. So I will look at that separately. So I don't want this session's recorded for class. So I don't want to.
All right. Sorry.
So what time? Question for Nye. What time is the exam? The exam goes all day. So because it's available to you all day, you can take it at any point from the start of the day till the end of the day. And then I'll set a time limit for how long the exam will be, and I'll make sure that you know about that time limit prior to the exam. Okay? You guys have to end the meeting for everyone, and then Mina, I will take a look at that and send you an email, because when I end this meeting for everyone, that includes you. It closes off.